right, the depressing number of 4 people in class out of 20. That's approximately the number of people probably going to pass the subject, as I see. But anyways, let's actually, jokes aside, let's actually start the session, and we'll see what we're going to do. So I am going to go through the few concepts today that are the very important kind of beginning of everything. We are going to have an overview over the whole C++ story. Then we're going to talk about C++ building blocks and then understand the compilation and execution. And that's going to be it. So I'm hoping that it's not going to be a very complicated session, but well, we'll see how things are going to go. So the main purpose of the 345 subject is the fact that it goes beyond OOP344. It actually builds over your 244 knowledge. I have 2 people over here. I'll give it to you. You pass it to him. Okay. Yeah, next time sit beside each other. All right, so yeah. So we're going to go build on your OOP244 knowledge, and then we're going to move towards more advanced C++ industry practices. The C++ has evolved in features from C++ 11 added to the features of C++. It made it more natural, flexible, and efficient. So our focus for the 345 is that to go beyond just using C++ as a better C thingy and kind of understand its power and then use it accordingly. So as an object-oriented language, C++ frames everything sets around objects that are interacting with within their problem domain. And that's essentially what an object-oriented program does. So when we talk about objects, they are essentially instances of what we call classes. Good morning. Instances of what we call classes. And classes are the basic encapsulated design of an object. So essentially, blueprint of an object becomes a class, and that class holds the essence of an object-oriented language. And I need to put this thing on do not disturb. There we go. Again, as I mentioned before, I have to keep my cell phone on. If I may have to receive a call, and it's going to stay like that till the end of the semester. My apologies on that. But please, you turn yours off, all 3 of you, and the people at home. Yeah. So these capsules in which we put the stuff in, they have 2 things that makes the thing encapsulated. One is the state of the object, which is essentially what we call it members and attributes. And the other ones are behavior, which are actually member functions, or what we call methods. Okay? So methods and attributes of a class. So methods essentially work on the attributes of the class itself. We good down to this point? We are just going, as I told you, slowly from OOP244, we are sliding into OOP345, reviewing everything very quickly, and then we're going to continue as we are going forward. So essentially, as I mentioned, I will always have the Visual Studio open, coming in with sample codes. As I mentioned, again, remember always you have to go to properties and set your properties. C++17 is a minimum, but I always set it to 20 just in case I use something that is. Okay? So essentially, what we have is something like this. Very simple, straightforward example of a class. I have a car, it has a speed. I have a constructor that sets the speed. Accelerate method changes the state of the object that increases the speed, and shows what is the state of the class. Very simple and straightforward. Example of actually packing the data and behavior together. So as you see, I'm going to over here write class example. This is how it goes forward. So that's the first example. And we go through and it becomes, and it goes to the next one and next one and next one. We have three core concepts of object orientation. We have three people, three concepts. One of them is three core concepts. If you don't know, we go past, you know that, right? Polymorphism is one thing, and the next one is, I know, I'm going to ask a person, somebody, actually, let's do this. So polymorphism is one of them, and now Jasmine is going to tell us what is the next one. See, if you're joining online, you need to be able to immediately answer the question when I ask you. Okay? Jasmine, are you there? If you cannot answer the call, do not join. Okay? Lily, how about you? Can you guys hear me?
So your question is polymorphism and...
We said three core concepts of object orientation. Yeah. The first one, our friend over here mentioned, it's polymorphism. And we said the second one, give me an example. What is the next one? You can say passive.
Abstract.
Pardon me?
Abstraction.
One more time?
Abstraction.
Abstraction, actually, very good point. Abstraction is not part of object orientation, but part of any programming language. We need to be able to do abstraction to be able to actually do anything. Abstraction essentially means taking the parts you want and the parts, and thank you very much for your contribution, Lily. Now, Abhishek is going to tell us, so we know abstraction is for any programming language. So far, we know the core concept is polymorphism, and Abhishek's going to tell me, what is the other one?
Inheritance.
Inheritance, thank you very much. And now my friend over here is going to tell me.
My answer was inheritance.
So it's polymorphism, inheritance, and encapsulation. You're not supposed to say it. You already answered one. It's in case things go, then you can come for rescue. But okay, anyway, so these are the three core concepts that we need to focus on. So continuing on the matter, so we have encapsulation. It essentially couples the data with the logic. Essentially couples the state of the object with the methods. Okay. And a weak encapsulation is when you make the attributes of the object available to things outside of the class, which is very bad. And the tighter the encapsulation be, it's least access to the state of the object, which is very good and nice. So remember, we want to always strong encapsulation, which data is private and integrity is preserved. Are we good? All right. Inheritance. When we talk about inheritance, essentially one class reuses and extends another class's architecture. So essentially a class is a blueprint. We know we have that one, and then we can get that class and improve it into another class. Very simple and straightforward. Example for it is something like this. So I have a class animal that can speak, it can make some sound, and now I create a dog that re-implements the speaking thingy and does a woof. Okay? So therefore, dog is an animal. Are we okay with this? It's very simple sample of inheritance. Keep forgetting to put return over here. If you don't put it, essentially it's going to return 0 when you don't mention anything, but let's not leave anything to defaults. All right, so in case the next question pops up, that's yours. So, next thing is polymorphism. When we talk about polymorphism, essentially it means what, my friend over there?
Doing the same thing in many different ways.
In doing the same thing in many different ways. I could not have said it better than that. So essentially when you do polymorphism, essentially you do the same thing in many different ways. If you remember the last lecture of OOP345, polymorphism comes in many different shapes. Remember that? 2 different shapes, major shapes. It was categorized into 2 main categories. Remember that? Anybody at home, do you remember it? Activate your microphone. 2 major concepts of polymorphism. Now remember, one was ad hoc and universal. Thank you. Thank you. Ad hoc and universal. Essentially, ad hoc was the things that when you look at it a little closer, you would see it's not polymorphism. They are faking it, if you recall, like overloading. Overloading is, it looks like you're calling the same function, but it's not. It essentially attaches the type to the end of the name, and that becomes that. Another thing was casting, right? We talked about universal polymorphism, essentially a real polymorphism where actually everything is identical and the correct method is chosen based on what you're doing. One was virtuality and the other one was template, right? So these are the aspects of polymorphism that we want to look at. So this is an example of inheritance. And going forward, looking at an example of polymorphism, we could actually look at this. Very simple example for it. I have an animal that can speak, but that speak is virtual, okay? Which means it cannot talk. And then we have dog that overrides the speak, makes it woof, and an animal that overrides, and a cat that overrides the speak says meow. So when I create 2 animals, one is dog, one is cat, when I say first animal speak, automatically the dog speak will be invoked, and for the second one, automatically the cats will be done. So at this, we will call it inheritance. So this is universal inheritance. And the question that I have, is the animal over there abstract or is it a concrete class?
Abstract?
No. You flip a coin. If it's not, so it is concrete. Why is it concrete? Because I could have created an animal. So I could have had create over here something like animal, A0, and I said a new animal. And there's no problem with that. I could have done that, and, oh. Why is it not oh, because I put a reference. Sorry, keyboard is a little, okay, anyway, so I can do this. There's no problem. Now A0 will actually, when I call A0 over here and I say speak, you know it's going to make some sound, right? We don't know what. It's going to make some sound. And that shows that actually my design is not really good. So if I actually run this program, we'll see that it is actually working and everything is being called properly 3 years later when it compiles and runs. Give it a second. There you go. So some sound, wolf and meow. Now, so this one is polymorphism. The next thing we need to talk about is modularity. We talked through that in OOP345 in detail, and we said that the source codes are divided into modules, and each module is compiled separately, and when the whole entire application gets recompiled, only the change module will get recompiled, and that's one of the very good features of modularity, especially when you have a huge application to compile. I remember that long time ago we had this, I don't know if we still have it or not, we had this open source project called Open Office, and it used to have something like Microsoft Office they created, but open source so everybody would do it. I remember that at that time with the computers that we had, it would take us 5 hours to compile it, 4 hours to compile it with the computer that I had. Okay, so it would take a long time. It was a ginormous amount of code, and compiling it would take a long time. But then after the compilation would have been done, and if you hacked the code and you changed something, you added some features, you recompiled, it would just take 5 minutes because everything is compiled and only the modules that are changed will be compiled. So, yeah. It essentially, when you create a repository, this is how basic type of repository works, which essentially you create different modules for the same application, and 5 people are working, and I'm going to say, okay, you work on the menu class, you work on the bill class, and you work on the employee class, and you work on the customer class. And all of you are working on the same repository, but you're not having any conflict because each of you is doing a separate thing, and when you push it, it doesn't interact. That's the best, cleanest way to collaborate. Sometimes, of course, you have to collaborate on the same course, and that's when Git actually comes into play, where you can have different versions and merge them when you want to. Questions down to this point? Suggestions? Objections? You good? All right. Okay. Now, building blocks of object-oriented programming, values, objects, variables, reference, functions, types, class members, templates, namespaces, and these all get together and help us write an application. Going through all these and to understand exactly what they are, we talk about types and the categories of types that we have. So we have, I think these are all supposed to be here. Again, I do not exactly follow what we have in here, but I think they mostly get covered. So I'm gonna, so what did I talk about? Yeah, so yeah, now we're jumping into types. So this is what I'm talking about now. So when we are talking about fundamental types, we are talking about types that are built in the language. So we have different types. We have the types and categories that we have. We have fundamentals, we have built-ins, we have user-defined, and we have concrete and abstract. These are the things that we have. Okay, these are the types that we have. The built-in ones are the ones that come with language. Okay, you cannot. They are what we call the atomic type of types that are created. When I say atomic, it used to be this thing that you cannot break a matter smaller than the atoms that it has inside, which is now physics kind of yeah, I know it went below that, but let's assume that's the smallest piece. It means you cannot break the thing lower than that. That becomes essentially built-in types like character, integer, double, things that come with the language, okay? And then we have built-in types. Built-in types are efficient wrappers around the fundamental types, like arrays. So when you create an array, that array are like a pointer. These type of things, they actually are wrappers around the fundamental types. These come with the language too, but they are usually packages or modifications or wrappers. When I say wrapper, and we're going to use this wrapper a lot in future, you're going to see we're going to write our own wrappers. When I'm calling a wrapper, I'm not talking about Drake, right? I'm talking about wrapping wrapping things inside another thing, like you're gift wrapping something. So the gift that you have, it's hidden inside, and then you represent it with some other wrap, and that represents what you have inside. So if you have a birthday gift and you put it in a Christmas thing, at the thing, you're confusing people. Your wrap doesn't match what you have inside, right? But if I have a birthday gift and I put a birthday wrap thingy around it, then I'm actually conveying the proper message in the yada yada and the matter of the surprise that I am trying to convey. Will be okay down to this point? Okay. So these are building types. User-defined types are using the fundamentals and built-ins to make new things, like an employee, like a school, like a car, okay? So they essentially use all these fundamentals to create something else. A concrete type is a type that you can instantiate, like animal over there. And an abstract type is a type that its representation is hidden, which means the object cannot get instantiated anymore. Because I have a pure virtual method, that's an abstract type. That type cannot get instantiated. Animal is a thing that it can speak. I don't know how. The representation is hidden unless I actually go forward and change it. We good? All right. Oh, I should have done this, I'm going to say. Error. And this is not needed. We good? Scope and linkage. Scope is essentially where you can see something. Scope, like right now I have 5 people in this class, and so the scope of my in-person class is 5 students, right? And the scope of my online people are 3, I think. It's 3. 1, 2, 3, yeah, 3. 4 actually. Yeah, 4. So this is the scope of this class, total of 9 people out of 18. 50% pass. That's good. Okay, so that's the scope of this class. If I actually mention someone's name and I actually say over here, for example, Liu, calling that person, hopefully that person's going to say hello. Satuhani, you there?
Yep.
There we go. So that's Leo. What? So I didn't need to say anything but Leo because we are in the same scope. Leo said hello. And hello to you, my friend. All right?
Hello.
All right. So that's it. So that's the scope, that everything is visible. So we have different types of scopes that we're going to go through. And linkage is when I'm going to say, go to room B3046 and ask Jane to come over here. That's the linkage I'm creating. So I'm giving you this message that not in our scope, but in a neighboring scope or some other scope, something, an object is there, go over there and grab it and bring it over here. That's what we call linkage. We good? You created that linkage last semester in your project. Let's see how many of you actually did the project yourself. You had a linkage over there. You had a class. Actually, never mind. We'll go. Doesn't matter. You had a utility, right? Utility class. That utility class you wanted to forget it. Anyways, we'll go through it. It's not a scope of OOP345, so we just created it over there, and probably you even didn't know that you're creating an external linkage, but you did. We'll come to it soon. It's amazing that we have a monitor over there. I don't know who's that for. Somebody who has eyes behind his back. Yes.
Was it an extern keyboard?
Yes, it was an external keyboard. Thank you. It was extern, yeah. So extern was actually what was creating an external link. Oh, well, that's when we are coming to all the good stuff we'll see. So, talking about compilers and type systems. So essentially compilers are translators of source code, and they create binaries out of your source code. When I say source code, that means human language. So C++ is human language, it's not a computer language. Take that out of your mind. C++ is human language, it's not a computer language. Okay? It is designed for humans so they can talk to computers. Compilers take that C++, they convert it to computer language, which creates binary files that are executable. Kinda, right? We good? Okay. All right, so that's that. So this is my backup plan in case things go wrong. That's my own desktop. If things go up wrong, I can actually use it. I used to use that all the time. Now I'm using the laptop. See how it's going to work out. Okay, so so it translates source code to binary code. Then we have language standards, which essentially ensures portability, which means I'm going to tell you, please set your C++ to C++20 or C++17, which means the code you're writing in this class, if you take it on a compiler that doesn't support these standards, it may not run. Okay, so the language standards are the things that you need to be careful about. And each language of its own has its own type system, which essentially wraps hardware-defined storage into an identifiable entity for you. Like, for example, when you say an int, it's essentially 4 bytes in memory. You don't care about that. For you, an integer is a variable in which you can hold a scalar value from minus something to positive something. But essentially, it's a wrapper around something that happens in a compiler. You see the difference between OOP345 and 345 now. We're kind of going through the detail to understand how these things work. So violating this type system can lead to undefined behavior, which means if you have a double variable and you put it in an integer pointer and then try to write something on an integer thingy, it's gonna, you don't know what's gonna happen because you are referring to part of memory that is designed to hold a double, and you're putting an integer in it, and it becomes identified behavior. That's why we have C++17 with type safety that won't allow you to do that unless you explicitly ask for it. If I go to good old C, I can easily do that and then shoot myself in the foot. But when you're coming to C++17, when you are doing that, you have to actually ask, hey, compiler, don't worry, I'm not crazy. I have some reason to look at this double as an integer for whatever insane reason that is. Okay? If you don't do that, compiler won't let you. That's called type safety. So we have compile time, we have link time, we have run time. What is compile time? Compile time is when you have written your code and you translate your code to binary, which means when you're writing a project with 5 modules, each module is compiled separately. Each one of these, so you have 5 compile times when you're compiling a program with 5 modules. When all these modules are compiled successfully, then you have to kind of concatenate these things together, attach them, link them together, make it one executable. That becomes link time. Okay? So things happen in different times. For example, if you define a variable, you don't define a variable and use it. If you write age is equal 25, but you don't mention what age is, that's a compile time error, which means it cannot understand what the heck you're talking about. Link time is when you say, I have a function called foo. So in your header file, you introduce a function called foo, but you don't implement it anywhere. It compiles fine, but when you try to link it, you said, you promised there is a foo. Where the hell is it? That's link time. The last one is execution time, where link time and compile time, they pass proper with no errors, And when it gets to executable time, you run it and you see instead of 5 times repeating something, you are repeating 6 times. So that's a logical error. Or you allocated some, without allocating memory, you tried to write something in somewhere. So you could have logical error. You could have system errors that you did not foresee. Okay? So that becomes the compile time. I'm sorry if I'm putting you to sleep, but these are the things that we need to know. And that brings us to static versus dynamic memory allocation. We always said that static is known as compile time, puts everything in a stack, where dynamic is determined at runtime and puts everything in heap. Okay? So essentially, this is what's going to be. Come on. So now, as you see, A is a static allocation. Okay? Again, static allocation, I'm not talking about a static variable. That's a different ballgame. Okay? With respect to memory allocation, I have static and dynamic. A is a static allocated memory, and B is a dynamic allocated memory. They're both fine, but one is in the stack, and the other one is in heap. We're going to go through it, and we'll understand exactly what they are. We good down to this point? Going through that, we have code segments that we put stuff in, like, memory segments. We have memory segments in which we put all these things together. So when we say dynamic or static, where do these things go? So memory that we have in a computer, it gets separated into 4 different entities. One, we call it code segment. What is code segment? Code is where main goes into. When you compile main into binary, it actually goes into a piece of memory which is later on fed to CPU, and CPU goes through and fetches each instruction and start executing that. That's code segment. That's the piece of memory that your executable is actually loaded into. Then we have data segment, which all the global and static variables will get inserted into, which is right beside your code. Okay? These are all loaded in memory when your program gets executed. We have stack segment that all the local variable goes into. Anything that you write integer A, integer B, that's the stack segment. And then we have heap segment that all your dynamic stuff will go into. And these are the segments of memory. Okay? So code, your code is it goes into. Data segment, all the global and static data variable that it goes into. Stack segment is where your local variables go into. And heap segment is where your dynamic variables go to. We good down to this point? So one more time, go through everything. OOP's baseline encapsulation, inheritance, and polymorphism. We have modular design that allows scalable programming and projects. We have building blocks of the language that are values, objects, types, functions, templates, and all the good stuff that we have. We have compilers that enforces the type system and compiles everything into code. And we understand what is the difference between compile time and runtime, and also understanding how memory organizes code, data, stack, and heap into operating systems so it can actually run stuff. Questions? Yes?
What is runtime exactly? Because I think understand compile is when you transform like the C++ language into binary, right?
You want simple version or fancy version?
Simple version.
Simple.
Just started this.
When you execute your program. Compile is when you write your code and you compile your code. On Linux, you say G++, yada, yada, you compile your code. The code is being compiled. Nothing is happening. Then you throw away your compiler You have the result of the compiler that is an executable. You run that executable. That's the runtime. So the errors that happen while you're compiling, these are either happening in compile time or link time, because compiler is essentially a combo. When you just write G++ and you compile, it compiles and links. Okay? But let me actually show you. So when you write a program, this is what you have. You have modules, 1, 2, and 3, and 4. So you have 4 modules over here. And then you have header files. But when you're compiling the compiler, these 4 arrows that you see, that's compile time. Where they compile, so the compile time happens 4 times. You have 4 compile times. Module 1, Module 2, Module 3, and Module 4. It gets compiled. No error, it goes to the second one. No error, it goes to the third one. No error, it goes to the fourth one. No error, it gets all the objects file created by compile time, links them all together as an executable time. When the executable is created, your compile time is over. Compile and link time is over. Now you can throw away your compiler and linker, and you get to your executable. Now you run your executable, and it executes, and hopefully it does what you design it to do. That becomes runtime.
Okay, I understand.
Okay. Thank you for the question. I swear I had something specifically for this. So that's the, let me bring it over here. That's not the one I wanted to show. Oh, there you go. So let's actually go to the next thing, which is, where did I put that? Oh, we talked about the building blocks too. Now compilation and execution. Okay, so compilation and execution. Oh, no, we haven't talked about these yet. Let's go through these. And then we have a separate section for compilation and execution. I'll go through it in detail, although kind of we talked about it almost entirely, but so when we are talking about C++, we have series of fundamental building blocks in C++ that we have that we need to address and make sure we understand. Again, as we mentioned, values, variables, objects, references, functions, types, class members, templates, namespaces, all the things that we have used in C++, we need to understand where they stand. So the very first thing we need to understand, what does it mean to declare or define something? What does it mean to declare or define something? To declare is to introduce something into a program, not necessarily define it. A declare is a function prototype. It doesn't specify what the thing is. A definition is the body of the function that tells what the prototype is doing. Sometimes declaration and definition happens at the same time when you say integer a semicolon. When you do that, you not only are declaring an integer, but also defining it too. You have an a that actually does something. So, in other words, we could say this is a perfect example for what actually declaration and definition is. External, remember? So if I say extern int x, I'm declaring no definition. No integer is created. Extern for a variable is like a prototype for a function. So when I say extern integer x, unless somewhere in some other translation unit, did I mention what translation unit? We're going to explain later. Unless in some other module that I have a global variable called x, that x is not defined yet. So if you use that x, it's not going to work. But when I say integer y is 10, now that is actually all together. I have an integer and it's a y, so both happening at the same time. Foo over here is declared. I don't have it. Bar over here is a definition with no declaration, which means if you go at top of bar somewhere, try to call it, it won't allow you because you did not declare it. The only way a function becomes declaration and definition at the same time if it's written before the caller function. You have experienced this in C all the way through in OOP345, but you'd never put a name on it. So this is essentially what it is. Declaration essentially means to introduce something to your scope and say, hey, I have this, trust me. Definition is to keep that promise and provide what that declaration was. We good? All right.
Question?
Yes.
So,
Give me a second. That first of all helps you think toward your thing and gives me a time to put it over here so we can record. Let's go.
So the declaration isn't just saying int x the same thing as extern int x?
No. Extern int x, if I right now go in bar and try to print x or set x to 5, it's going to fail. It's going to tell you, I don't have any x, I can't find x. Where the heck is x? You're not going to get a compile time. You're going to get a link time error. So when I write x is equal to 0, it will trust me. But when I actually want to link it, it's going to tell me, you told me there is an integer x somewhere. I don't see it. Unless I have another module somewhere that it has a global variable called int x, which this one, consider that one as an external. Remember I told you Jane from B4034, another class, right? If I do that, now I'm creating an extern. So you trust me, there is a student called Jane in B34, whatever, another class, right?
Yeah.
Now this is compile time. You don't get any error. Or I'll tell you, there is a tutor down in Learning Center. You trust me, life is beautiful. Compile is done. You say, I have a problem. I go to the tutor. Now the link time happens. You actually have a problem. You go to the Learning Center, no tutor. You give me a link here, right? You told me there's a tutor and why it's not here, right? Got it? So that extern for a variable is a promise. It's not an actual definition. You need to create a global integer to actually do that. You good?
Yep.
So I don't know if this works or not. Okay, let me try something. Okay, I'm just looking at something for a second. I'm sorry, I'm trying to close a few things in here that are open for no reason, and then I'll continue. I just wanted to give you an example of that, but of the actual extern stuff. We're going to go through it. Let me just finish this, and then I'm going to come to all that. Give me a second. Let me. Just a second. There we go. So let me bring these over here. So I have a module. This module essentially is a display for a student, and whatever this student is, and I have module, yada, yada, yada. I have a minimum pass grade that is a global scope, and this one is a file scope. You'll see why that's a global scope soon, okay? And this one is file scope, okay? Now, I'll come in here in module.h, and as you see in module.h, I have a student actually created that has all the student stuff. Forget about this volatile, I'll explain later. But I create an extern constant int minimum pass grade. This declares the prototype for the min pass grade that can be accessible anywhere. So the global variable inside module that I call minimum pass grade is not only accessible to this translation unit, to this module, it's also accessible to whoever includes module.h because that is introducing it. Therefore, if in my program in here, I have something like this, I saved this, right? This is, no, I did not save this. So let me save this. This is declare and define. So now in here I am including module.h. Because I'm including module.h, I can simply say if mark is less than minimum grade, do this. It's not defined here where it is. It is in module.h that it's telling there is a minimum pass grade. Trust me. So when this module is compiled, I don't get any error. At compile time, it gets this module and module.cpp at the same time. And because the minimum pass grade that is promised in the header file is actually provided here, then the main can actually access it. So minimum pass grade is truly global, where maximum standard student number length that is 9, it has a file scope, but it has a potential to be global if it is declared. If it's only defined, then it's file scope. It's only defined in this class and declared in this module. And that is everywhere, anywhere that module is included. Am I making sense? How do you use see in and see out?
How do I see in and see out?
How do you use see in and see out? See in and see out, they are instances of iStream and OStream, right?
Yeah.
How do you use them? Do you create them?
No.
Where is it created?
It's created in the library files.
So how do you have access to it?
I include the logic.
Thank you, because they are externed in the IO stream.
Yeah, yeah.
They instantiate it in the library, then they write extern O stream C out, extern I stream C in. Therefore, you have access to them anywhere IO stream is included, you can access them.
Yeah, I get this idea, but what I don't get is the difference between extern and just having it normally.
Let's do it like, can I use maximum student number length in here?
No.
Why? You just told me what the difference is.
Can you go back to the module.h file?
Yeah. I don't have an extern for maximum student length.
Yeah.
Therefore, I cannot use it here.
Where is it declared, the max student length?
It's in module. It's declared and defined at the same time.
It's declared in module.cpp.
Yes. So
Yeah,
only module.cpp have access to this.
Yeah, but if I declare it in module.h, then I can use it in main too, no?
If you include module.h, can you use it in anywhere else? Do you see this being declared in the header file?
No.
Going back to the picture I showed you. This is actually important, people. I don't joke around this, because this is essentially what you need to understand perfectly. And I don't care, it's going to take time. Add existing item. Paste. So when you look at the compiler, these are your modules, right? Can 3.cpp use anything from 1.cpp?
No.
Why? Because it's not included in there.
Yeah.
Therefore, if I have some global variable in this CPP, I cannot use it in here if it's not external. But 2.cpp's header file is included here, right?
Yeah.
Therefore, if I have a global variable over here and an extern in a header file, 3 can use whatever I have in 2 that is externed. Does that make sense? That extern is the declaration. Okay?
Yeah.
I have a question.
Yes.
So we used to like use define, hashtag define. What is the difference between that and external?
What is it defined between, what is the difference between define and extern?
Yeah.
First, no relation.
No relation.
No relation. Number 2, have you ever written something in, say, Microsoft Word, and or you're writing an email, and you tell me he did this and he did that and he did that, and then you look at the thing, oh my God, it's a she, not a he. What do? You do a search and replace for all the he's and replace them with she, correct? Right? That's literally define.
Okay.
Define happens when? At compile time. Actually, not compile time, it's pre-compile time. Not even compile time. We'll come to it soon when I explain. So I said we have compile time, run time, and execution time. Now actually we have pre-compile, compile, link, and execution. Define happens at pre-compile time, which means before the compiler even begins to compile your C++ code, it goes through all the tokens you have defined to something else, removes them from the code, literally, and replaces them with what you defined.
Okay.
Then it starts compilation. So it has nothing to do with C++ language. All the code you start with a hashtag, they are not C++. They are C++ compiler's language. It instructs compiler what to do before compilation. Am I making sense? All right. Good questions are coming. I'm happy. I'm happy. It's a good day. All right. All right. So in here, I'm going to say F usage of external linkage. Okay. Where was I? One definition rule, a variable function class template must have exactly one definition. Otherwise, it's going to fail. It's not going to work, right? You cannot say integer A5 and double A is equal to 2.5. It doesn't make sense, okay? Exactly one. And if you have two, then you're going to get a compiler. And hence the compilation safeguards. The if define, if define, and end if that we write in every single header file, that protects the one definition rule, which means it only gets compiled once. Again, because it starts with hashtag, it happens before compilation. Compiler checks, is this thing included already? No, so let me compile it. Is it included already? Yes, I'm going to ignore it. Okay? We have block scope, class scope, namespace scope, global scope, all these good scopes that we have. We have two of them over here. So this is global scope. This is file scope, which means only accessible in the module and nowhere else. This is global because in the header file, I externed it. You see that? Because using external linkage, I actually made that global. We have, let me see if I have, example for, I do have it somewhere. So, scope, I think this is the one. Yeah, this is not bad. So let's put this one over here, prg.cpp. What the heck is this? Okay. I have too many things. Let me just close it down. Close all tabs. Sorry, I had too many things over there. I just don't want it to be messy. So as you see over here, in here I have a function scope, which essentially means I is only defined in main and nowhere else. Okay? Then I have a block scope, which is essentially this integer that is defined in the first block of if, after that it's dead. And then I have I, and it's after that is dead. But these two i's shadow the outer I. So at line 19, when this is printed, the value of I will be printed. That is what is user entered. So what user enters at line 10 has nothing to do with I at line 12 or I line 16. I line 12 is a separate integer at I line 16, and the two shadow in the scope the I that is entered by the user. Okay? And this applies to every scope and inner scope, which means if you have a class, your class has an attribute called I. Then inside the method of a class, you create a local variable called I. Then the class's I will be shadowed by it. Remember that. It not only with an if and a main, it happens with a method and its class. So you can easily shadow stuff. You have to be careful with naming. That's why it's a standard rule in Seneca that we write all our member variables or our attributes with an M underline at the beginning. So we are essentially tagging them that these are member variables, not to shadow them by mistake. Okay? It is a very common practice in many companies. Okay? They have different rules and regulations, but this is one of them. What are the other scopes? Class scope, you know what it is. Namespace scope, essentially because names can collide in different, we have done it in OOP345. In the namespace, you can actually create definitions, and because of the namespace, it's not going to have any problem. Shadowing, we've talked about it. Linkage, we talked about it. External linkage, we'll talk about. Oh, internal linkage, we did not talk about. External linkage is when you extern something, so it can be shared. So external linkage is this. So this was scope. So this is external linkage. So I have something that you can share it somewhere else, right? And as you see, it's a global variable that the definition is here and declaration is up there. So anywhere you write extern int share me, the global variable will be shared. That's external linkage we talked about, right? Oh, I have two F's. So this is G. G. And this is EFGH, and this is external linkage. Now, you can enforce something to only be accessible in a module and nowhere else. If you do it like this, is one of the usages of the static what is the name? See, I got blank. Modifier. Static modifier, okay? So when I write over here static int local, you see that in one class, and static local 2, it becomes impossible. You cannot extern these. This local variable is in module B, and this local variable is in module A. They are separated. This is a literal example of file module, to enforce a file scope. To enforce a file scope, so here is, again, I don't want to write two different files. We understand that that's CPP, right? There are two files. So this is enforcing. So only in module A, only in module B. So these are enforcing. So if in a test I ask you, how can I enforce a variable to only have file scope? That's how. Okay? And that's going to be a question in your quiz. You good? I have to remind myself to put that thing actually in your quiz. So. Oh, come on. Give me a second. These are important stuff that I put it over here separately. Every semester I bring a new one, so this is the one that I have to write. Quiz question 345. How to enforce file scope using static modifier. Okay, so that's that. So I'm going to call this EHI, internal linkage. We good? All right, we talked about fundamental, built-in types. We know all those things. Just want to make sure that we're good. Yeah, this is a good example for it. So the difference between fundamentals and built-in types. So as you see, integer x and double y, they are fundamental types, but built-in types are the array, reference, or enumeration. We're going to learn this soon. what is enumeration, and what is color, let's see, that is red or something like that. So color is actually enumeration. We'll see that. So these are built-in types. They are still within the language definition, but they are built. If you think about it, these are ingredients, okay? This is the recipe that compiler applies. Custom types are things that you cook using all these, okay? IJ, so I would say fundamental versus built-in. I'm sorry that I don't give you a break because I need that time to run to the other class. I have a 5-minute space and I have to run from this class to another 3, 4, 5 and set everything up. So no break for neither of you. Those people start 10 minutes late, you're gonna end 10 minutes early. And I have 20 minutes to run from one class to another. Therefore, our class ends it's 9:45, right? So we're gonna end that. So come here, please, with coffees, like big, like espresso, double espresso coffee. Come to the class. Thank you. People at home, are we good or we are deep in sleep? Give me a thumb up. We are in deep sleep. Coma. Completely gone. Oh, there you go. One person, two. And Jasmine is deep sleep. Gone. Okay. All right. So the good thing is I get an assistant over there too. Attendance over there too. So we have that one. The qualifiers, we have constant, volatile, and constant volatile. Constant variables are variables that cannot be changed. If you set them as constant, it essentially means that they are not changeable. Okay. Volatile is a little difficult to explain with our level of knowledge, but there are things that are hardware dependent. Variables that are hardware dependent, which means when you write an integer and change its value, you change its value. You know, if you set it to 2, it's 2 afterwards, right? But when you set up a variable, and that variable is a register of the CPU. Who knows what is a register of a CPU? Anybody knows what's a register of a CPU? Did they tell you in the first semester stuff? No. I don't want to go in. Let's say you have a network card. A network card is passing information through internet, right? And it has this piece of memory in which all the network packets are written, right? Now, if you name that piece of hardware place that the network information is sitting in, and you use that as a variable in your program, that value is volatile because it may change any time but by a piece of hardware out of your control. Those are volatile variables, variables that may change. We have no use for it in OOP345. Just remember that they are out there, okay? When you do hardcore hardware programming, like graphics card programming and things like that, it becomes handy. Type defines. It comes from C language, where you were forced to reuse the name of structure when you were creating something. In C, when we said struct employee, to create an instance out of employee, we had to say struct employee E, right? That's why we had type def over it. What type def does essentially says you can actually get a type that is in C and rename it to something else. It becomes an alias for the exact same thing. So if I say const int, that becomes an alias for it, for constant integer. What is a good thing about it? I'll give you an example right over here for you. So say I write over here integer pointer A and B, okay? A over here is an integer pointer, but B is not. B is an integer. Did you know that? So if you write integer pointer A, because this asterisk is something that is added to, it's pretty weird actually. So we think that they are both integer pointers. They are not. B is a regular integer. Okay? So I'm going to actually write it like this. So I'm going to write it like this. So I'm going to say over here, so this is equal to address of val, and this one is equal to a value. Two different things. This is a pointer. This is an integer. Do we understand this? But if I did this, but if I did this, now, if I write over here int ptr, p, q, this is equal to address of val, and this is equal p and q, and this can be equal to address of b. So they are both pointers. You understand the difference now? What happened? So, no, you didn't?
No, I lost you at the end.
So we said that when you write a built-in type, this is not a fundamental type. This is a built-in type. It's made up of an integer to create an address. Therefore, int is the type. When you write integer pointer A, this integer pointer only affects the variable that is coming. The other one is affected by int. So essentially the comma takes the int, not the asterisk. But when I package the two and name the entire thing as an integer pointer, then when I write int ptrp, it's not a define statement that searches and replaces. It literally is a compile time type that is an integer pointer. Therefore, p is an integer pointer, q is an integer pointer. On the same line. Okay? The message that I'm trying to convey is that typedef literally creates a type. It's not a search and replace like define. If I did a define, it would have been the same. Actually, that's a beautiful question for a quiz too. What is the difference? So I'm going to have a typedef and a define, and I'm going to tell you which one is what. Okay? That's another question to understand the difference between typedef and define. Difference between typedef and define. So I told you I only do programming questions. The things that you see over here, these become multiple choice. Okay? Multiple choice and fill in the blanks thingy. So I use this and give you 2-3 questions like that. Okay? Everything. I try to, actually this is the first time that I'm doing this. I'm trying to have all the concept questions coming from the lectures. So like this, I kind of enforce students to actually listen to the lectures. And the new modern type of typedef is using the using phrase. So essentially using int alias int is the same thing as saying typedef int alias int. The two are the same. This is a modern type that came with C++. This doesn't work in C. Okay? So this is modern alias that came with C++. Are we good? We okay? Please take a look at the notes that I have written over here. They may not be in the subject notes. I'm not 100% sure. So make sure you look at them both. So JK, type def, and alias. Yeah. All right. You already know namespaces. I'm not going to bore you with it. You've done it, namespaces. The only thing that I might want to let you know is that you can, you have used namespaces using namespace std, but if you don't want to bring the entire thing in, you can say using namespace std scope resolution iStream. So you can bring pieces of a namespace. So if I have this, I don't want to. So if I have a namespace like this, okay? Again, these are separate files, okay? So if I have a namespace like this, in here I can say using namespace SD to bring std in, and in here I can say dot leader s, right? To actually specify that I'm dealing with the namespace dot. But I could have, instead of writing this, I could have said using namespace, using dot leader. So you can actually write this. So essentially this means I am only using, if I say leader over here, it is coming from dot. Is it leaders or leader or leader? Okay? Does that make sense? Okay, so that's that. Just keep that in mind. What I wanted to say? Yeah, that's that. Okay, good. JKL namespace. We have storage lifetimes, variable lifetimes, object lifetimes. Object lifetimes fall in 4 categories. 3 of them you understand. 4th one you will understand at the end of the semester. The first one is automatic, which is essentially a block variable. You put it in a block, the block is over, the variable is gone. That's automatic. The second one is a static one. It's not the static to make things global. If you actually create a static variable inside a block, it becomes global, but only with respect to lifetime. The visibility is inside the scope, but it stays alive. Essentially, so what happens over here, phi is better. Let me take this. Let me take this here. Phi is easier to understand. So if I call phi over here, okay? What happens is that the first time for is called, S is declared and defined, and it becomes 1. 1 is added to it, it becomes 2. The very first thing that is printed is 2. The second time for is called, line number 12 is completely ignored. Because it's static, it means it was created before and it stays alive. Now S has 2 in it, it becomes 3 and 3 is printed. Am I making sense? Okay, that's this static as local is different with static as enforcing file scope variables. We have 4 different types of static. Number 1, static that enforces the file. Number 2, static that remains alive in a scope. The third one is a static method, a static member variable, an attribute. We'll talk about it later. And then we have a static method that we're going to talk about that later too. But this is with respect to lifetime. Okay. All right. Let me see, what else do we have to talk about in here? We're good. Now, the last thing we are going to talk about is compilation. Understand what compilation is and go through, where is it? Stages of compilation. So essentially, when we are compiling, we have the picture over here. Stage of compilations, we have first pre-compilation, which essentially expands all includes and does all defines. So the first pre-compile, it actually includes the header files inside the CPPs. Okay? Anything that you include literally means copy and paste. Literally. Okay? For that, I had an example. Let me put that up. It doesn't hurt if I do that. So, okay, so I'm going to bring 2 files over here. So I'm going to right click over here. I'm going to say add existing items. And I'm just going to paste 2 files over here. Didn't I copy? Copy. What? Okay, paste. Okay, Boo Boo and Hee Haw. You see that? Okay, so let's. I'm gonna click on add. And I'm not gonna add it actually. Just spread it over here so I can show you. Look at Boo Boo over here. Boo Boo over here has include yada yada OP. Let me take that date out. It's incorrect. It's 8 actually. Okay, so as you see, it's a halfway thingy. It doesn't make sense, right? And then if I look at Hee Haw over here, it's again doesn't make sense. It's halfway of a program, right? And I'm just going to remove, I'm going to remove these 2 from the project. I'm not going to delete them. I'm just going to remove them. Sure. Did I change? Oh, yes, I changed. Okay, so I just removed them. I didn't do anything. I just removed them, right? Now, if I go to main, and in main, I do this. I have include Boo Boo, include Hee Haw. That's it. That's my main. If I run this program, it actually runs OOP345 week 1. How? Because it's a blind copy and paste. It copies boo-boo in, it should be able to open, go to document. It opens this one at the beginning and then pastes this one as second. Where is it? Therefore, I'm going to have a complete program. So again, includes are nothing but copy and paste. Remember that. When you are saying, I'm going to use a library by, you are not including anything. You are just bringing the declarations inside. That's all includes do. They copy and paste. That's why avoid random includes, because you are bloating your source code for no reason. Only include when necessary. Okay? So that's pre-compile. And then after that, we have compilation, which is compiling and then linking. And that's that. So we went through all that. You know exactly what it is. I'm just going to bring this one up for you so you can see. So you have a source code, preprocessor happens, expand includes, replaces macros. Then translation unit, which essentially means each module is compiled and the outcome will be the object files. At this stage, compilation is over. Then it goes to linker, combines all the objects that are created together, creates an executable, and then after that you have everything executed. We good? That's compilation. Now, how the compilation commands are and stuff, please go read it. It's in the notes. I don't want to write over here what a compile line is. You know that, right? Questions? Let me actually add this thing to your, these are my notes, teaching notes. I'm just going to, this one, the other ones don't make sense because it's just messages for me to talk about certain things. If I put it for you, it's just going to be confusing. But these ones are actually useful. So I'm going to put it over here. So compilation pipeline diagram, I'm going to call it. Copy. And I'm going to add it over here. Add existing item. Control V. Oh, cancel. No. Control V. Yeah, so I opened the wrong file. So this is essentially what I just showed you over there. Questions? Suggestions? Objections? I'm going to ask you a question. I want an honest answer. People at home over here, and please don't think that I'm going to get offended and stuff. I just want to try and see, test something over here to see what's going on. Okay? So from a scale to 1 to 10, how did you understand the session?
I give it
6?
7 or 8.
7 or 8?
6.5.
6.5? 8?
Yeah,
So, because half of it he was asleep. Okay, I'm joking. It's early morning. People at home, send it in the chat so I can see what. Give me and it's just for me to know. Believe me, if it's more than 6, I'm a happy guy because usually that's what the lecture is supposed to be. You need to be a 6 at the lecture. Go home. Did they tell you about the curve of forgetting? Okay, study proves,
No.
and research proves that if you want to commit something to long-term memory, what you need to do, when you get a lecture, an hour lecture approximately, or a session of lecture a day, what you need to do, in the same day, you should spend around 20 minutes reviewing what happened. Then the week later, spend 10 minutes. Then the month later, spend 5 minutes, and it's committed to your long-term memory. First day, 20, 1 week, 10, month 5, and it's committed to your long-term memory. Obviously, you're going to come back with questions. If that 20 minutes makes it stick, fine. But if it doesn't make it stick, you come with questions and so on and so forth. Okay? So remember that. 20, 10, 5. 20 same day, 10 next week, 5 month later. Done. You will remember it for the rest of your life. Okay? It is proven. I can send you that paper for it, but I don't want to waste your time. That's the gist of it. Okay? So in a text, please, in a chat, please send me, again, that level of understanding. I would appreciate it. I have a 7, and a 7, I guess. 7, I guess. All right. Thank you very much, everyone. That's it for today. I have to pack and quickly go to the next session. Have yourself a beautiful day, and we'll see you during the lab. If there is going to be a quiz, I'll let you know. If not, it's going to be next week. Hopefully, today we are going to post the workshop that is due in 2 weeks. Have yourself a beautiful day. Bye-bye, everyone. Bye, everybody at home.
Thank you, ciao.
Cheers.